Welcome back. This is episode 6, part 2 of everything you need to know about JPEG. This is a direct continuation of part 1, so there's not really much need for a review. Let's just jump right into it. So we just finished implementing Inverse DCT, and it works, but it takes way too long to run. What we've done is we've implemented the textbook definition of the summation of the Inverse DCT for a two-dimensional 8x8 matrix. But if we're going to improve the speed of this function, we need to abandon the textbook definition. But first, let's start smaller. There are two major problems with this function. One is that we calculate two cosines per pixel, and cosine is a slow operation. So we want to reduce the number of times we need to compute cosine. The second major problem is this quadruple nested for loop. For every pixel, we have to traverse every pixel. So before we think of ways to optimize this, let's get a better idea of exactly how bad this is. We've mostly been testing on this JPEG file, which is approximately 680 pixels by 450. That's a good medium-size image. It's not incredibly small, but it's not incredibly large either. Let's test our Inverse DCT on a much bigger JPEG file. Here we have a JPEG file called turtle.jpg, and it's approximately 4,000 by 3,000 pixels. If we try to run our decoder on this JPEG file, it will take minutes. It'll take way too long. It's not even worth trying. However, we can get a pretty good speed up for free just by turning on compiler optimizations. So now with this, let's see how long it takes our decoder to process turtle.jpg. Instead of just running this on turtle.jpg, let's time it by passing the command to the time utility. And I'm just going to cut forward because that took almost 17 seconds. That's awful. For any kind of real image processor, 17 seconds is useless. Before we start the optimizations, I'll just say that instead of calling these variables j and I, it's much more conventional to call them u and v. So to stick with convention, let me just rename those real quick. So j and cj were renamed to u and cu, and I and ci were renamed to v and cv. Really, the important part is that x pairs with u, and y pairs with v. We can also squash all of this down to just two lines. If v is equal to 0, then cv equals 1 over the square root of 2. Otherwise, it equals 1. Okay, so now enough with the distractions. What can we do about cosine? One thing you might notice is that anytime we calculate a cosine value, the only variables used are x and y and u and v. And these variables are completely predictable. We know that all of them will go from 0 through 7. The real unknown variables are the inverse DCT coefficients that are inside the component, which are not used to calculate cosines. Since the value of the cosine is so predictable, we can pre-compute ahead of time all possible cosine values that we know we'll need. If we just look at the first cosine, since x goes from 0 through 7 and u goes from 0 through 7, that's 8 possibilities times 8 possibilities. That is 64 different cosine values. For y and v, they take on the same values as x and u, so it's the exact same 64 cosine values. So let's just pre-compute all 64 cosine values at the start of Inverse DCT and never compute cosine during the Inverse DCT of a single component. So let's do that right here. So let's make an array of size 64 and we'll call it IDCT map. And let's fill this array with the cosine values for just one of these two cosines. So let's just use x and u. And let's switch to floats because we don't really need the precision of a double. And that looks just like this. We can also pre-scale all of the values in the Inverse DCT map by the coefficient c, so that we do not have to multiply by c every time in the main loop. And we push x inside the for loop, so that we don't have to calculate c as many times. The calculation of the cosine is exactly the same. 2 times x plus 1 times u times pi over 16. all multiplied by c, and that is the inverse DCT cosine value at position ux. The other thing we can do is eliminate this division by 4 by sneaking in a division by 2 into the coefficient c. So the value of c is 1 divided by 2, or 1 divided by the square root of 2 divided by 2. So let's provide the inverse DCT map to the inverse DCT component function. So what does this map do for us? Instead of computing the cosine, we can index into the map at position ux. We can do the same thing for the second cosine, except we'll index into position vy. Because each of these cosine values factors in CV and CU already, we don't need to include them here. And because each of these cosine values is already divided by 2, we don't need to divide the final value by 4 anymore. And since we already changed everything else to a float, let's change this to a float. So let's see if this is any faster. Remember, a minute ago, it took us 17 seconds. And this time it took us 3.5 seconds. So we got a huge speed increase just by doing all of our cosine calculations at startup. But 3.5 seconds still isn't very good. What we really need to do is avoid a quadruple nested for loop. We can accomplish that by instead processing all of the columns and processing all of the rows separately by doing one-dimensional inverse DCTs on all the columns and doing one-dimensional inverse DCTs on all of the rows. It will make the code lengthier and a little bit less straightforward in terms of what it's doing, but in the end, more efficient. So for now, let's just get rid of this. First, we need to perform one-dimensional inverse DCT on all of the columns. So for column I, we need to move down the column and process every YV pair. For every Y position, we need to compute a sum of cosine values. So here we need to initialize sum. For every value of V, we need to add to sum the cosine value in the IDCT map at position Vy, just like before, and we need to scale that cosine value by the inverse DCT coefficient in the component at position Vi. And that looks just like this. The cosine value at position Vy scaled by the DCT coefficient at position Vi. Once we have the final sum, we can store it in the result at position Yi. Once this is finished, we have calculated the inverse DCT for every column of the component and stored the result in the result array. Now we need to perform inverse DCT on every row of the result array and store the result of that back into the component. Because of this, let's change the result array to an array of floats so that we don't perform rounding right in the middle of our calculations. So this looks extremely similar. I represents the row number and x moves along the row. For every x value, we need to calculate a sum. To calculate that sum, we need to consider every xu pair. We grab the cosine value from the map at position ux, and we scale it by the DCT coefficient that is now in the result array at position iu. Once we have that sum, we can store it back into the component at position ix. So now we have 2 triple nested for loops instead of 1 quadruple nested for loop. Let's see if it's any faster. With the quadruple nested for loop, it took about 3.5 seconds to process turtle.jpg. Now it takes about 1.5 seconds. That's definitely a lot better, but we really want to be able to process an enormous JPEG file in under a second. How could we possibly do that? The answer is that we need to abandon the idea of this summation altogether and go with a much more optimized solution. Two of the best resources on this subject, in my opinion, come from unixforlife.org. There's an article on the two-dimensional discrete cosine transform and the one-dimensional discrete cosine transform. It starts out by talking about the forward DCT, which we can skip. Here we see the definition of the 2D inverse DCT, which is exactly the same as the first implementation that we tried. This section at the bottom talks about how you can optimize the naive implementation by performing DCT on the rows and columns separately, which they've called row-column decomposition. This is the same as the optimization we just tried implementing. And lastly, it mentions an algorithm called AA&N, which, as far as I can tell, is the most standard, well-known algorithm for JPEG decoding. However, their example here only uses AA&N to perform forward DCT, and they don't have any code example of how to use the AA&N algorithm for inverse DCT. So we're still going to have to come up with that on our own. The other article they have goes into just a little bit more detail. What we're really interested in is this section at the bottom, again about the AA&N algorithm, and this time it includes a diagram to help illustrate what this algorithm does. So let's take a closer look at this diagram. The AA&N algorithm also decomposes the MCU into its columns and its rows and performs one-dimensional DCT separately, so we'll stick with that new structure that we just wrote. But what we do per row or per column is very different. What the AA&N algorithm does is it takes the 8 input values, which are the 8 values along the row or along the column, sends those values through this flow graph, and computes the final output values. The whole point of doing all of this is to incredibly reduce the total number of multiplications, additions, subtractions, etc. that have to be done, and to eliminate the need to ever calculate a cosine. Here's what we need to know about how to read this graph. Values travel from left to right, from node to node. White nodes are just a pass-through, so basically no operation. So the value at this node is the same as the value of the node preceding it. Black nodes are additions. It is an addition of the two incoming lines on the left side. So the value of this node is the value of this node plus the value of this node. Arrows mean a negation, so the value of this node is the value of this node here minus the value of this node. And lastly, big boxes are multiplications, and the value inside the box is a constant that we know ahead of time. So the value of this node is the value of this node times the constant A1. And that's really basically it. But again, this is for the forward DCT, so this doesn't directly help us. However, what is incredibly convenient about this is in order to come up with the flow graph for inverse DCT, you only need to read this flow graph backwards. So if these were our input values and we travel from right to left through this graph, the final values of these nodes are the output values. You can simply Google AA&N Inverse DCT flow graph to find some examples of the mirrored flow graph. This one right here is my favorite, so let's take a closer look at this one. And here we go. So this is basically a mirrored version of the forward DCT flow graph with a couple tweaks and optimizations made. For the forward DCT, if we say the starting point is column A, then this would be column B, column C, column D, column E, column F, and column G. So for the inverse DCT, we start with column G and move towards column A. The big catch about this graph is we don't actually start with column G right away. Each incoming input value needs to be multiplied by some factor to get us column G. So the input values are actually scaled first in order for the rest of the flow graph to make the correct calculations. In fact, every input value is actually scaled by a different amount, determined by this expression here. Also notice that our output values are in the order 0, 1, 2, 3, 4, 5, 6, 7, but the input values are 0, 4, 2, 6, 5, 1, 7, 3. That reordering of the inputs is just so that these rails are nice and straight all the way through the graph. So all we have to do is calculate G0 through G7, and then move on to the next column. Calculate F0 through F7. Now the next column, the E column, we have to calculate E0 through E8 because there's an extra node hanging down here. Same thing, D0 through D8. And in addition to that, there's these two extra nodes hanging out in the middle right here that don't really cleanly fit in a column. So actually, I'm going to clean this up a little bit and make my own version and make a couple tweaks and label everything the way we know we want it labeled. So this is the flow graph we're going to be using instead. I've more clearly labeled the scaling factors at the front before column G. Input 0 is scaled by S0, input 4 is scaled by S4, and so on. Once we have column G, it's very straightforward to compute column F, column E, column D. With column C, I eliminated one of those two extra nodes in the middle, but we still have one awkward node that isn't in a column. But let's just label it C8 in our code. So we'll calculate C0 through C7, and then calculate C8, which depends on C5 and C6. Once we have the B column, everything crisscrosses and we calculate the A column, or in other words, our final output. So we saw a minute ago that these scaling factors were actually the result of a cosine, but all of those cosine calculations can be done ahead of time, so it doesn't hurt the runtime of the algorithm. We'll see in a minute that the same is true for the M factors. There's a cosine buried inside these M factors, but all that calculation can be done ahead of time. So that's really it. Let's get started. So first, let's start by adding the S factors and the M factors to our header file. S0 through S7 are defined exactly the way we saw. The M factors we haven't seen just yet, but they're pretty simple. M1 and M3 are actually equal to each other. M0 is not actually used in the algorithm. M0 is only used to calculate M2 and M4. So here, what do we need to change? We are still going to process every column, followed by processing every row, but instead of calculating the inverse DCT by performing a sum, we'll simply use the AA&N flow graph. Another benefit of this is we can actually do the calculation in place. So as we process a column or a row, we can store the result directly back to the MCU component, so we don't need this temporary storage location anymore. And since we've eliminated the need for computing cosines for the algorithm, aside from our factors, we don't need the inverse DCT map anymore either. So first, we need to calculate column G. I is the column number, or the x-coordinate, so our 8 inputs are chosen by changing the y value to pick all the 8 values that belong to column I, and we scale them by the corresponding S factor. Then we compute column F. These first 4 are white nodes that just let the value pass through. It's technically redundant to make extra constant values that are just equal to other constant values, but it's not really going to cause a performance impact because of the compiler optimizations. And these 4 are black nodes that add to other values from column G, some of which have negations. Then we compute column E, which includes that extra E8 that's kind of hanging below the graph. Then column D, which is just when we do the multiplications by M1, M2, M3, M4, and M5. Then column C, which has that extra odd case where C8 is dependent on other C values, unlike everything else, like all the other C's, which are dependent on D values. Then we compute column B. Then lastly, the A column, which is really just the final output, which is when all of the B's crisscross, and we store the results straight into the same 8 positions that we originally read from at the start of all of this. Then we do this all over again on every row, but the calculation is identical. The only difference now is that I is the row number, or the y-coordinate, So we grab all x values as our 8 input values, and then store the 8 result values back into the same 8 locations in the MCU component. And that's it. So if we just shrink these really ugly loops, Inverse DCT is just this. Let's see if that improved the speed at all. Last time we ran this, it took about 1.5 seconds. And now it's 0.9 seconds. That's pretty good. I think that's enough optimization for us for now. There are still 2 major optimizations that I'm aware of that could be done, but I'm pretty happy with under a second. One thing we could do is push all of these multiplications by s into the dequantization step prior to inverse DCT. Since the dequantization step has to visit every single DCT coefficient and scale it anyway with the multiplication, we can save time by doing all of these multiplications at once. The other thing we can do is use nothing but integers and bit shifting so that all these multiplications are actually multiplications between integers rather than floating point numbers, and we can preserve the precision of our result by bit shifting before and after those multiplications. In my opinion, those 2 optimizations hurt the readability quite a bit, and while I'm certainly trying to keep efficiency in mind, I also want to keep the code very readable and informative. So I'll pass on those 2 optimizations for now. But I certainly encourage you to look into that if that sounds interesting to you. I suppose before we end this, we should still validate that we haven't broken anything. So if you recall from the end of part 1 of this episode, this is what cat.bmp looks like when we perform inverse DCT on it. So let's just make sure that when we run this now on cat, we still get that same output. Which now takes 2/100ths of a second, by the way. And we still get the same output. And by the way, this is what turtle.bmp looks like after inverse DCT. Even though the colors are all wrong, it's very nice that we can see the lighting, we can see the shadows around the shell of the turtle if we compare that to the original. So even though the colors are all wrong, that really strongly indicates to us that we have correctly transformed from the frequency domain, the DCT coefficients, to the spatial domain, or the color data. So there we go. That is all for this episode. All we have left is the color transformation. Thanks for sticking with it all the way to the end of this episode, and I'll see you next time in episode 7.